Welcome back to this module on exploiting TLP to improve the throughput of a single core. The purpose of this lesson is to review software multithreading and to give an introduction to hardware multithreading. Actually, this idea of multithreading is an extremely old idea. It is already used in any operating system we know of. For example, in any multi-threaded or multitasking operating system, we hide the latency, the extremely long latency of I/O operations by trying to execute multiple processes in a time-shared manner. This is illustrated here. On the left we see that process P1 is running and then it performs a system call for input-output. At that time the operating system is running for some time and schedules another process, in this case process P2, which can then make use of the processor cycles. And hopefully by the time the processor 1 executes again, the I/O has been completed, so process P1 can continue. That means that in the operating system, every time the processor does an I/O, the processor does an I/O operation, the process, which is the currently running program, is preempted and removed from the list of processes that are ready to execute from the ready list. The I/O operation is started. Another process is picked, another ready process is picked from the ready list and is allowed to execute. And when the I/O completes, the operating system is informed of that and puts the preempted process back in the ready list so the next time it can execute again. The problem with doing this in software in the operating system is that we need a context switch, and this takes an extremely long time because we need to save the entire state of the process, and this includes the current value of the program counter, the current register values, etc., etc., and store this entire process state somewhere in memory, in a data structure typically called the process control block. At least that's what it said in the Linux source the last time I looked at it. And we need to restore the process state of a different ready process and start its execution. That means we need to flush the pipeline, we need to fill the pipeline again, and also the caches will not be warmed up, and this all attributes to the long cost and the high cost of a context switch. So what we need to do is to make the cost of a thread switch smaller. We want to be able to run multiple threads on the same core really in parallel. So we need to implement the context switch in hardware. And the minimum support in hardware we need is to replicate the architectural states. So all running threads must have their own hardware context. That means that the CPU, the single core, needs to have multiple register sets, one for every hardware thread. And it has to have multiple state registers, such as the program counter, the interrupt factor, etc., etc., because it only concerns a single thread. When do we start the execution of a new thread? We can run a different thread each time a thread is blocked. That's basically the same we do in software at the operating system level. What does it mean for a thread to be blocked? For example, if it tried to synchronize, but it was unsuccessful, or if there was a level 1 or level 2 cache miss, then while this thread is waiting, we should run another thread or when there was a translation look-aside buffer miss. Even while waiting for operands to hide the latency of, for example, floating point operation, we might decide to run another thread so that the latency is hidden. Roughly speaking, there are three types of hardware multithreading. The first one is called coarse-grained multithreading, also called block interleaving. That's basically what I describe here. We start another thread when the current thread is blocked. Another approach is fine-grained multithreading, also called cycle-by-cycle interleaving. That means that every cycle we fetch an instruction from a different thread. And finally, the most advanced multithreading approach is simultaneous multithreading, called hyperthreading by Intel. Then we try to issue instructions from different threads at the same time to different functional units, like we do already in a superscalar core. Simultaneous multithreading matches very well with a superscalar core. I will discuss in the lessons to come each of the three different hardware multithreading approaches in turn. This completes this lesson. Thanks for watching. In the next lesson we will look at block multithreading, also called coarse-grained multithreading, which is a form of core multithreading which starts executing a new thread when the current thread is stalled. Stay tuned.